Hi, everyone. Thanks for joining us for the next session of our RAG Deep Dive series, RAGChat Optimal Retrieval with Azure AI Search. My name's Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. And while we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is being recorded. It will be available to view on demand within 24 to 48 hours right here on the Microsoft Reactor YouTube channel. With that, I'd love to turn it over to our speakers for today. Thanks so much for joining us.
Hello, everyone. Welcome to our RAG Deep Dive series. This is number 3 in the series, but you're welcome to join at any time. I'm Pamela Fox from the Python advocacy team, and you're going to see me a lot in this series. But today I'm joined by my first guest speaker. Can you introduce yourself?
Hi, everyone. I am Hannah Gonzalez. I work in the relevance team at Azure AI Search. I'm a software engineer.
Awesome. I love it when we get joined by engineers and product managers and folks that are actually on the team. So Hannah will be talking later about relevance, which is a lot of what we're talking about today. So for those of you who are new to this series, we are doing now 11 sessions, 11 live streams, diving deep into our most popular RAG solution for Azure. And it's a very, very full-featured solution that combines AI search with OpenAI with lots of optional features. So it's got multimedia ingestion, it's got chat history, it's got user login, data access control, speech input and output, private networks, evaluations, just so many different features. So that's what we're doing in the series, is diving deep into the solution so that all of you can understand the code that goes into writing a great RAG solution and can feel really powerful with that code. So this is our third session. If you missed the earlier ones, no worries. They are all recorded. You can go back and watch the recordings and ask any questions you have either underneath the video or in our discussion forum for the repo. And even if you missed the early ones, you can totally join us here today and you're still going to learn quite a bit. So today we're going to be talking about how to do optimal retrieval with Azure AI Search and everything that goes into all the search options. So there you go, our topics for today. So let's start with just to recap an overview of this RAGChat solution that we're diving into. It is an open source solution and it builds on Azure OpenAI and Azure AI Search, and you can deploy it to either Azure Container Apps or Azure App Service, whichever works for you. It is the backend is all written in Python and the front end is all written with TypeScript plus React. And as you're saying, it does have quite a few features. So you can grab the code from aka.ms/ragchat. That'll bring you to the repo with all the code and all the documentation. There's lots of additional documentation here as well that go into all the different questions that people ask about all the different ways of using it. And then you can even check out the live demo. So I've been deploying this all morning to make sure that all the demos are up and running. So, let's go ahead and click on one of these questions here. So this demo is asking questions on our sample data, and our sample data is like a bunch of pretend HR documents for companies. So in this case, it has like a role library that describes what a product manager does. Like, okay, well, what does a CEO do at Contoso, right? So we can ask different questions, about, specific to the data here. So you are all welcome to check out that demo and try it out and see how it works. And this is just with the basic features. There's other demos that have the other features enabled. But even the basic features, you can see that you've got stuff like citations that you can open up and you can view the citation, the PDF, on the side and see where it got the data from. You can look at the thought process and see, oh, okay, so this is what happened first, and then it searched, and then it went and made a call to the LM. So you can see how all of this works in that demo. So today we're going to be diving into the search part of it, because the search part is actually a huge part of it. So RAG stands for retrieval augmented generation. And retrieval means, finding the information that we need to answer the question. And it turns out like retrieval is like the most important part of RAG. Like if you can get really good retrieval, then you can generally get really good RAG. So that's why it's so important to really understand how to retrieve things from your knowledge base and how to do that best when using Azure AI Search. Oh, and here, just to reiterate, let's look at the flow that a question, this question can take in the chat app, right? So, we ask a question, we get an answer, we ask a follow-up question. The first thing that happens is that we actually send that follow-up question to an LLM in order to rewrite that into a query that incorporates like the past information. So then we get back a good query like, oh, okay, Northwind Health Plus plan coverage for eye exams and hearing. We send that, suggested query to AI search, and we get back results from the AI search index. And then we send both the user's question and the history and the search results all to the LLM and say, hey, please answer based off of that, off of that information here. And that's how we get a great answer. So yeah, we really want to understand how to use Azure AI Search so that we get great retrieval. And that is what Hannah is going to go into now. So I will switch over. Oh, wait. I forgot that first we're going to talk about vectors. And the reason I talk about vectors first is because we are going to use vectors and so many different aspects of this RAG flow here. So first, let's make sure that everybody is on board with vectors, because really a lot like vector embeddings are new to most people. I think most of us didn't use vector embeddings in before 3 years ago. So just want to make sure that we all are on board with vector embeddings. Okay, so a vector embedding is where we take some input and then we get back a list of floating point numbers. And that input could be a single word, right? So traditionally the word to vec model would encode a single word. It could be a text string, right? So the OpenAI models will encode text of up to about 8,000 tokens. Or it could even be image or text if we're doing like a multimodal embedding model like the Azure AI Vision model. There we can even give it an image and get back this list of floating point numbers, right? And then the list we get back, they have different attributes as well, right? So they all have different lengths, right? So with OpenAI, the original one was 1536, but now the new ones are anywhere between 512 numbers long to 3072 numbers long. And generally, like the more numbers that are in the list, the more information it's encoding. But it also takes more space to store those, right? So we ideally want to be able to encode as much semantic information about something in the minimal amount of space. That's always the goal with vector embeddings, is to try and encode as much as we can in the minimal amount of space. So how do we do that? How do we actually make a vector embedding? So here I've got code using the OpenAI SDK. So, I connect to my OpenAI account, to my Azure OpenAI deployment here. And then I can encode something. So here I've got this sentence about a dog walking past my house. And I say, hey, make an embedding based off this sentence. All right. And then I can take a look at the vector and you can see that it is a list of numbers here and it's quite long. It is 1,536 numbers long. So that is what we call the dimensions of this vector. That's for the text embedding ADA 002 model. If I used one of the newer models, the text embedding 3 models, then we would actually pick the number of dimensions we want, and it would be some other number, between 256 and 3,072. And the important thing is that like dimensions are different per models, but also all of these embedding models all have their own embedding space. So whatever you use for your embeddings, you then need to use those embeddings like going forward, right? You have to be consistent with the embeddings you use because they all have their own embedding space, right? It's kind of like taking a brain. We have different brains. So text embedding 8002 is a particular brain that thinks about the world a certain way, and the other models are different brains that think about the world different ways, right? So now once we have embeddings, we can then use that to figure out how similar two things are, right? So imagine we have this sentence, the new movie is awesome. And then we have these three sentences that compare it to. So we have the same one. We have a very similar sentence. This recent movie is so good. And we have an absolutely nonsense sentence. So we can compute embeddings for each of these and see what is the similarity between these vectors. And there's different ways of calculating similarity. Here we're using this calculation called cosine similarity, which is generally a pretty good metric to use. And so what you can see here is that we got a score of 1 for the same sentence to the same sentence. So a score of 1 means, hey, these two sentences are the most similar possible. Then we see a score of 0.91 for a very similar sentence, right? So this new movie is awesome versus this recent movie is so good. That got a 0.91. So that's quite a bit of jump from 1.0 to 0.91. And now for the nonsense sentence, we see a score of 0.74. So this is really interesting. Once again, this is with the text embedding 8002 model. So what you see with that model is that generally the scores range between around 0.7 and like 0.95. You don't usually get that much lower than 0.7, and you don't usually get that much like higher than 0.95 unless you're looking at the exact same. So that's just for this model. In its similarity space, generally the vectors are like kind of clustered. I heard it described as an ice cream cone. So imagine like an ice cream cone of vectors, and so you're only going to get as low as about 0.74, even for something that's actually really, really different. So this is my first point, is that when you're looking at cosine similarity scores, you're not necessarily looking for absolutes. Like you're not looking for a 0.0 to mean that they're completely different. You're looking relative, right? So relatively, this sentence is much more similar to this sentence than this sentence. That's what we know from the scores, is relatively how similar things are. Okay, so now we can actually start doing searching, right? So what we can do is load in a bunch of movie titles. These are Disney movie titles, and I've already calculated their embeddings, so I can go ahead and show you that file, right? So we've got embeddings for all of these movie titles. And then what I can do is I can search those movie titles with any query I want, right? So I'll do like a movie about cute puppies. Okay. And I take that query string and I convert it to a vector. Then I compute the similarity of that vector with the existing vectors, and then I can get back the results. So here we see that the top rank is Teacher's Pet, and then Beverly Hills Chihuahua, Piglets, Snow Dogs. 101 Dalmatians actually ranked lower than some of those earlier ones. But I guess Chihuahuas are cute to some people. Let's try cute kitties. There's actually not as many cat movies on Disney, which really disappoints me. But yes, Aristocats is our favorite cat movie in this house. There's just not enough of them. You got the Tigger movie. But this thing is, you can search for anything, right? We can even do different languages, right? Because these languages, so una película sobre gatitas, yeah? And see what we get back. We should get similar. Oh, let me expand this. Ooh. Here we go. And same thing, right? So, I just translated that to Spanish. So generally these language models tend to be multilingual as well. And so that's a nice bonus you get from it, is that if you are trying to, build something that works for people from other languages, depending on the language, you might be able to just use the same model, which is really cool. Okay. So yeah, so that's why we like to use vector embeddings, is because they can search for things, and they can find things even if like the text doesn't match at all, right? So there's no overlap in the actual words in this query, but semantically, in the semantic space, this query is the most similar. The vector for this query is the most similar to the Aristocat. So it was able to find that even with no overlap at all in the actual words used. So that's what people love about vector search, is that the ability to find things regardless of exact spelling and exact words used. Okay, so that's the intro to vectors, right? So here we were talking about vector similarity, right? Looking at the distance between the vectors here, seeing how close they are, and then using that to do vector search. So this, vectors are a big tool that we're using these days, very powerful. They also have some gotchas. So we're going to see how we can use those in Azure AI Search for our optimal retrieval. All right, so now I'm going to go over to Hannah to talk about Azure AI Search.
Great. Thank you so much, Pamela. So I'm really excited today to talk to you about Azure AI Search. I am Hannah Gonzalez, a software engineer from the Relevance team. And let's start by talking about what is Azure AI Search. So Azure AI Search is a comprehensive search solution that supports everything that you need to build a search engine. And it also includes features specifically built for RAG applications in mind. It is also enterprise ready, which means that it is secure and it has everything that you need in order for you to deploy it into your enterprise. And it is also integrated with open source packages that are very popular, such as LangChain, Semantic Kernel, Llama Index, as well as Azure services such as Azure OpenAI and Azure AI Studio. So basically, whenever you're building your RAG application, you can use Azure AI Search. Great. So now let's go over a notebook that will let us take a quick look on how Azure AI Search works. So in the beginning, we set up an Azure Search client using the Python SDK. Then we will be creating an index. We'll be using a small index at first. So the name for our index is teeny tiny index. And we have several fields for our index. So the first one is the ID, which is sort of like the primary key for this index. Then another field is the embedding, which means that it's a vector of 3 dimensions. And this just means that each vector in the index will have 3 numbers in it. And then the vector search that we'll be using for this index is the HNSW. We will go over this later in the presentation in more detail. And then we just create our index. So now that we have our index, let's insert a few documents with small vectors. So in this example, we're just inserting these 3 vectors. They just have random numbers on them, and we're inserting the 3 of them in our small index. And now that we have documents in our index, now let's search using vector similarity, which is what Pamela was saying earlier, of cosine similarity, of observing how close 2 vectors are to each other. So for example, let's take this input. So this random vector, let's see which of these 3 vectors is closest to our input vector. So we search it and we get the result that the vector with ID number 2 is the closest to our input vector. So typically, we will be using larger indices. Much more interesting vectors with possibly larger dimensions. So what we do here is we also initialize Azure Search variables with an OpenAI client. We are just connecting to our larger index. In this example is the index with the HR dataset that Pamela was showing you earlier. So in this example, let's look up this query. So learning about underwater activities. So then this text query, we vectorize it, and then we search it. And then we see that we get this as our top result. So scuba diving lesson and surfing lesson as our top result, which is semantically similar to our query, but it's not the same as in keywords, just similar. So with that, that's our demo for Azure AI Search. So now let's go over our vector search strategies that we talked about in the code. So the first one is ANN, which is typically what we want to use. ANN stands for approximate nearest neighbors, and it is the most popular these days. And the algorithm most popular is HNSW, which stands for hierarchical navigable small worlds. And this method is great in terms of its performance, and it's also very efficient. It's also customizable, so you can tweak its parameters in the Azure AI Search configuration if you wanted to. And this is typically what you will want to work with because it makes the queries much more efficient and faster. And this is especially when you're working on making a user-facing application, because you will want faster results for your users. But another approach is called the exhaustive KNN search. KNN is just the K nearest neighbors, meaning that you will calculate the distance from your input vector to any other vector. And typically, you don't want to do this because it will take a lot more time, but you might want to do this if you want to create a baseline to evaluate how well your search engine is working. Another scenario that you might want to do this is if you're filtering down to a small number of vectors. So the amount of time that it will take is a reasonable amount of time. So you have these two options as vector search strategies, and you can switch after initial setup as well, which is an advantage too of Azure AI Search. Let's go over another additional capability that you can use in combination with vector search. You can use filters. Filters can be particularly helpful because you can filter out metadata, for example, or timestamps, like you can see on the example here. You can also do multi-vector scenarios. So you can have multiple vector fields. You might have a different embedding for your title than for your description. So you can send out multiple queries and have Azure AI Search merge those results for you. So next, we'll be talking about hybrid search. So in some cases, having vector search is not sufficient for us to obtain the most relevant results. So what we can do in these cases is to have full hybrid search. So we do a vector search with the embedding, and then we also do a text search with the keywords. And then we merge those results with an algorithm RRF, and we finally apply a re-ranking model that sorts the results based on the user query. And this re-ranking model is called the semantic ranker in Azure AI Search, and it is based on the same technology that Bing Search uses. So let's go over an example here on our notebooks to show this. So let's first set up our API clients. We set up an Azure OpenAI client, and then we set up an Azure Search client here. And let's go over an example where vector search is not always the optimal result. So in this example, our search query is $45, and this is the string. And you can see here that when we do a vector search and we make that embedding for this $45, we're not finding any relevant results. This is called exact matching. And vector search is usually not very good at this. For example, when you're looking for numbers, like in this case, or when you're looking for specific names, IDs, emails, etc. So another thing you might be thinking is, maybe there is no document that has $45 on it, and then that's why I'm not getting any relevant results. So let's see if that theory is true. When we compare it, this exact same search, but instead of doing a vector search, let's do a text search for the same query. So we didn't vectorize it like this. We just search it with the text itself. And then we see that the first match that we get, the first result, is the $45. So in this case, a text search has better results than a vector search. So what can we do in cases like this? We can use a hybrid retrieval, and we're using R and F to merge those results at the end. And RRF is reciprocal rank fusion. So what we're doing here is using both the embedding and the text. And then you can see here's the text and here's the embedding. And then you can see that our best result is at the top here. So $45. But it is not always the case that hybrid ranking is the most optimal. So let's look at that example. So when our text query is learning about underwater activities, and then we make an embedding of that query, and then let's see our results. So the first one is not related to any underwater activities. But if we take a look at our fourth one here, that's the one that's related to underwater activities. So in this case, hybrid ranking was not optimal. So what can we do in this case? Let's use semantic ranker. And the semantic re-ranker will take, we do first a full hybrid search like before, but then we re-rank it with the semantic re-ranker. So here's our text search, our embedding, and then we search it with the re-ranker. And then you can see here that our best result is at the top, just like we expected. But also note that some of the results here are not related to our user query. And this is where a score would be particularly useful, having a threshold to this score here. So let's go back to our slides. So like in that last example, we can precisely avoid noise with a minimum threshold. So the semantic ranker assigns each of the results a score from 0 to 4, with 0 being the worst quality and the worst possible match, and 4 being the best quality and the best match. So if you find that your application is often finding low scored matches, you can set a score threshold and filter out the matches that have a much lower score. So to further visualize this, here is an example of the most optimal relevance by using hybrid search plus semantic re-ranker. So let's see, our query is, what underwater activities can I do in the Bahamas? And we're doing a hybrid search. So first we look at the keyword results and then the vector results. So in our keyword results, we're getting a look at this exact match, Bahamas and Bahamas, scuba diving in Bahamas. And then in our vector results, we're getting, for example, scuba diving in the Caribbean. So notice that in the vector results, we're not getting any exact matches. We're getting results that are semantically similar to our query. So now that we have these results, we use our RF to merge these results. So here's how we merge them using RF. And then you can notice that the most relevant result in this case would be the scuba diving in Bahamas. But in this case, it is marked as the second position instead of the first position. So what we can do here is we can use the semantic re-ranker in order to fix this. So we use the semantic re-ranker, and then it bumps the score for the scuba diving in Bahamas being the most relevant, which is what we wanted. And then notice that it also dropped irrelevant results. For example, this last one here, it's not appearing anymore. And this is why the threshold comes into play and is relevant here. And the Azure AI Search team has done a lot of research to verify that this is indeed the best flow with the best results of using hybrid search plus the semantic re-ranker. And I encourage you all to check out the blog post with the results of the newest re-ranker. It was released very recently, and it has a lot of great updates, like raising the NDCG at 3 score by 22 points. Thank you so much. I'll pass it back to Pamela now to talk about RAG in AI search.
Pamela, you're on mute. Don't be.
Thank you, omnipotent one. Oh, omniscient one. All right. So thank you so much, Hannah. We've had lots of great conversation in the chat about AI search, and good discussion there. So now you've seen AI search and the basics of how to use it in Python, and that seeing that we want to use hybrid search with semantic ranker to really get the best results across all scenarios. So now let's bring it back to RAG. So here is a simple RAG flow in Python. Let me go ahead and open the notebook version of this over here. All right, so at the top, we set up all of our connections. So here we're just using the OpenAI SDK and then the Azure Python SDK for Azure Search so that we can connect to our OpenAI and also connect to our search. So that's all set up. That's the boring stuff. And then we get a user question, right? So this is what does the product manager do? And I turn that into a vector using my Azure OpenAI model. And make sure, once again, we got to make sure that when we turn it into an embedding, we're using the same model that we used when we made our index. Okay, so our models have to match. That means right now I'm saying, right now I'm using text embedding 88002. But really, that's an older model. I should switch over to one of the new ones, the text embedding 3 models. But it's kind of a lot of work to switch over because you actually would need to either build a new index or add a field to an index, like your embedding 3 field, and then add all the new ones there. And then once you had everything newly vectorized, then you could search against it. So just make sure that your embedding is always matching. The same exact model, same exact dimensions. They all need to match. Then we can take our user question and also the vector version of it and do a hybrid search and use semantic ranker in order to get back the best results. And then we just take those results and turn them into a nice string that we can send to the LLM. So here you can see our string has the file name and the page number. That's all from our index. So for each of our chunks in the index, we store the file name and along with the page number so that we can cite both of them. So we put that in square brackets, then we have a colon, and then we have the actual text from this chunk of the document. So each chunk that's in our search index is a chunk from a document, and it's usually around 500 tokens big. So we've got 3 chunks here. So here's another chunk. And then there's one more as well. Okay, so now we've got our chunks and they're nicely formatted. So finally, we are going to send a message to the LLM. So we say, okay, you need to answer only with the facts listed in the list of sources below. If there's not enough information, say you don't know. This is actually really important. My colleague did a test with leaving this out, and and he found that the LLMs were very happy to answer questions that they didn't know. So it's really important that an LLM says it doesn't know. So you need to empower it to do that. Say like, hey, if there's not information, just admit it. Just say you don't know, right? And I even, I reiterate there. I said, do not generate answers that don't use the sources below. And then I describe how I provide the sources. So I say, okay, each source has a name followed by a colon and the actual information. Include the source name for each fact you use. Use square brackets to reference the source. For example, square bracket info1.txt. So most of what we're putting here, all this, in this system prompt is about making sure it stays on sources, making sure it knows what the sources look like and how to cite the sources. And it's really important that we get it to properly cite the sources, because then in the front end, we want to be able to turn those sources into clickable citations. So we want it to provide those sources in a good, reliable format. All right, so then we take the user question, we combine it with the sources, and we send that to our chat deployment. I think this one is a GPT-3.5 Turbo or GPT-4o. And let me go ahead and make that temperature 0.3, because usually we use a lower temperature for RAG. Temperature is approximately equal to creativity, and we usually want a little less creativity with RAG. So we'll do 0.3, and we'll send that along here. All right, so here we get back the response and we say a product manager is responsible for blah, blah, blah. We can see citation, citation, citation. So this looks like a good response. It's giving stuff from the sources. It's citing where it got those sources. It's using exactly the format of citation that I wanted. And so then when this gets rendered in the actual app, these will get turned into clickable citations. So that's a basic RAG flow. We used a more advanced RAG flow in the app itself, but that shows you the basic RAG flow with using the Azure AI Search. So let's see it just once again in the the application, like the one I just did. So what does a product manager do? I go ahead and ask the application this, and we see actually a very similar answer to what I got in the notebook. That makes sense. And we can see the citations here. We can look at that thought process, and we can see that first it did the search, and it did a hybrid search with semantic ranker. We can see the scores that come back. So you can see a re-ranker score here of 3.8. That's a very high score, because remember, re-ranker scores are between 0 to 4, with 4 being the best. So 3.8 is very good. We can look at the other, the other ones. We got a 3.5. That's still pretty good, and a 3.5. So these are all very highly ranked scores. And then, we send this all to the LLM and get back the response. Now, in the application, we have all these settings that we can use. So we might say like, okay, let's set a re-ranker score and say like, if anything's lower than 2.5, just drop it, right? Like that's usually 2.5 is a pretty good threshold, but of course you need to experiment and evaluate. We could set our temperature, as we're saying, like usually 0.3 is what I use, but you could try a little higher, try a little lower. You could retrieve more search results. We're only retrieving 3 right now. But, if we're willing to spend a little money, a little more time with our LLM call, we could retrieve 5, we could retrieve 6, 7, 10, whatever. Like usually between 3 to 10 is the amount. We can decide if we want to use semantic ranker. We usually, will, because it will get the best results. We could even try out different modes like just vectors or just text. But usually I'm going to keep, semantic ranker with hybrid on here. But we have all the options so that you can test all this out and see how things are going, especially if you're running into like problematic queries, right? So you can try out different things and seeing like, okay, well, what if I change these parameters here? How do things improve, right? And if you do change the parameters and just think like, oh, maybe this is a good set of parameters, you do want to evaluate those new parameters. And I'm going to talk about evaluation in a few weeks in a session all about evaluation. But this is a great place to start manually experimenting and seeing, how things affect your results. And then there's also the chat tab, and saying this one does a little more of an advanced RAG flow that has an initial step here where it rewrites the query into a search query, right? And then does the search, right? So this is particularly useful when we have a follow-up here where we say like, oh, what else do they do, right? So if I'm saying what else do they do, that on its own is not a good search query. So we say, okay, here's the conversation history, here's the new question, and the LLM will turn that into a better query. we got a really long response there. Okay, so if we look at it this time, it takes this thing, what else do they do, and turns that into product manager responsibilities. So that's a much better query for our search index than the user's question, what else do they do, right? Which is completely lacking in context. So that's why whenever we have multi-turn RAG or a conversation with multiple messages, we're always going to start with this query writing step that's going to fill in missing context here. Okay, so we've seen now how AI search is used in the chat and how you can customize it with those developer settings. You can also, of course, customize it with the code. So generally, you're going to find all the code for the searching in approach.py. And here you can see I've got it right open to it. So here's our search code. So this looks very similar to what we're doing. There's a few extra options that we allow you to specify here as well. But generally it's what we're showing with doing a hybrid search. Okay. So there you go. There's the developer settings that we talked about. And now let's talk about data ingestion. So how did we get these chunks of data in our search index? And what are the best practices for ingesting our data? Oh, that's a funky thing. Okay. So first, let's talk about the manual ingestion process. So this is the process that our RAG repo uses by default. And basically, when you deploy it for the first time, it's going to look for all your documents in the data folder, and it's going to run this manual ingestion process in order to get them indexed. So the first step is to use Azure Document Intelligence in order to process the documents and get text out of them, right? And Document Intelligence is really good. It supports all kinds of formats. So PDF, HTML, DocX, PPX, XLX, images. And if it's got diagrams or images in there, it'll try to OCR the text out of it. So it tries to get as much text as it possibly can out of your documents. So we get the text out. Then we use Python code in order to split that text into chunks. And we try to split at sentence boundaries. We try to have an overlap of 25%. We try to make chunks that are about 500 tokens long. We have a lot of code in there that tries to do really good splitting. Then we can upload the documents to Azure Blob Storage. Then we take both the text chunks, we take those text chunks and we send them to Azure OpenAI and say, hey, turn these into vector embeddings. And finally, we take both the text chunks and the vectors of those chunks, and we store them in Azure AI Search along with the file name and page number. So that gives us everything we need in order to do those search calls later. So people ask, why do we even need to split documents, right? We go through a lot of efforts to split documents, and there's two reasons why we do it. So the first reason, and the original reason, was that a language model generally has a limited context window. So, the first models had 4,000 tokens or 8,000 tokens. And that was how many tokens you could send to the model. So that meant if your document was greater than 8,000 tokens, then you just couldn't send it to the model at all, right? So we needed to split to even be able to send information to the model, especially when dealing with long documents. There's also the case that every token you send to an LLM costs you money, because with LLMs, you're paying per token. So you don't want to have to send your entire novel to the LLM to get an answer unless absolutely necessary, right? And then the other reason is that the research has shown that if an LLM receives too much information, it can get easily distracted by all that additional information, right? It'll get distracted by anything that's not relevant to that answer. And it's going to be more prone to hallucinations or just not answering properly. So as a result, we generally want to send only the information to the LLM that it needs, but we also want to make sure that information has enough context for able to fully answer the question. So the question is, we have these documents, how do we split them? What's the optimal way of splitting? How big should those chunks be? So we have this research here in this blog post, which we'll link in the chat, aka.ms/ragrelevance. And in that research, they actually tested different token size to see how good the retrieval results were. And what they saw was that the optimal size was 512 tokens. So that's what we now recommend, is to have document chunks that are around 512 tokens. And if you're new to the token phrase, that's the unit of measurement we use when we're talking about LLM's input and output. And generally, it's about 1 token per word for English, but the ratio gets a lot higher for other languages. And it also just depends entirely on the model, right? So there's another great blog post about that that my colleague wrote, where he looked at the token ratios across different languages, especially like Chinese, Japanese, Korean, Arabic. And you can definitely see how that, token per word ratio changes. So that's why we talk in terms of tokens and not in terms of words, because tokens is the unit of measurement for a model, and they don't actually know about words. And then what is the strategy? When do you actually break, right? So they did different tests, like breaking at sentences, breaking with certain overlap. And what they found was the best results were if they had 25% overlap in the chunks, right? So that there's always overlap in the chunks of, 25%. So a little bit over, a little bit under. And with that 512 token amount. And of course, trying to preserve sentence boundaries, trying to preserve table boundaries, any kind of boundaries you can come up with. It's usually good if you can preserve them, but it can be hard because maybe you're going to go over that 512 token size, right? So it's all kind of a balance of wanting to preserve boundaries while also wanting to have reasonable sized chunks. I see a question about this. Can we use Power Query or SQL and Fabric to split them, or is Python PySpark more efficient? I did do a Fabric RAG workshop where we used like a Synapse library. Can I find that Fabric workshop? We used a Synapse library for text splitting. There we go. So that workshop is in here. So you can see how we did it for this Fabric workshop. Let me find it. RAG. Okay. All right, generating, storing, loading, and pre-processing. All right, so here we used a splitter. Yeah, I think it's there. So it's somewhere in this code here. But that's all I've done with Fabric myself. So the thing to keep in mind with splitting is that you need code that's going to do the splitting, right? So in our repo, we have our own code that does it, and you can see it's got like all these sentence boundaries and all this logic for preserving boundaries and stuff like that. But there's other splitters you can use. There is the splitter that Fabric has. There's also in LangChain. If you're using LangChain, the best one to use is the recursive character text splitter with the token option to do token based instead of word character based splitting. So generally, I would say splitting is hard. So I actually do not recommend writing your own splitting code. I think it is generally better to use other people's splitting code, but you do want to keep in mind, stuff like how good is the splitting code? Is it adhering to the boundaries that you want it to adhere to? Does it work well in the language of the documents that you're splitting? Right. So keep all that in mind. But yeah, there's lots of packages out there that you could use to do your splitting, and you just want to make sure that the splitting quality is high. All right. Yeah. Okay, great. So let's keep talking. Okay. All right. So we have 2 data ingestion options for our repo, and also just generally, if you're building RAG with Azure AI Search, you generally have a few different options for how you're going to do data ingestion. So the first option is like manual ingestion, where you're writing the code and you're running that code, and that code is all like running on your machine, or maybe it's even running like in a container app or a container app job or something. But like fairly manually going through all of it and doing each of the steps, in like a Python script, right? That's the manual ingestion process. Versus integrated vectorization, which is using cloud-based ingestion running entirely on Azure, running either on Azure AI Search or on Azure Functions using skills. So there's generally the options, though there's also things in the middle. So we'll see. But let's talk a bit about cloud-based ingestion. So with Azure AI Search has this notion of indexers, where the idea is that you can take wherever your stuff is stored, whether it's blob storage or data lake or wherever it is, you can connect an indexer, and that indexer will be able to check that store and see if there's any new data, and then index that new data. So it'll like keep track of whether there's something new and decide to index that new data. So Azure AI Search has a bunch of indexers for all the different Azure things. So that's something that you can use in order to have this periodic or trigger-based indexing of particular data stores. So that's a really popular thing that people use with Azure AI Search. Then you can set up skills, and skills are these code that you can run on the documents that come out to then influence how they get stored into AI Search. And these are usually deployed as Azure functions. So an Azure function will like run some bit of code, and that code has some input and has some output. So you can imagine that you have your indexer, and then you send the results of the indexer to a particular skill, and then that gets sent to another skill, and then finally the index has everything it needs in order to store the fields. So we have this notion of skills. We can make custom skills. We can also use built-in skills. Now, integrated vectorization is this AI search feature that is specifically designed for RAG data ingestion using a set of built-in skills. So, the first thing we set up is an indexer. In this case, we do it to blob storage. And that indexer will crack the files as needed, whether it's PDF or Office or images or whatnot. Then it has a built-in chunking skill. So it's got its own chunking code. We were just talking about chunking and splitting, right? So AI Search has a built-in skill for splitting. And it actually does character-based splitting right now, but you could change it you can customize it to token-based splitting. And, that'll do the splitting. And then the next step is the built-in vectorization skill, which will turn those text chunks into vectors. And then finally, they'll all get indexed into the index. And you can set that up in our RAG solution. So if you want to use integrated vectorization for the RAGChat repo, you can do that following the documentation. Now, here is my table comparing your options here, right? So whether to do manual indexing code or integrated vectorization. So the manual indexing runs on your local machine. I know many people will set it up to run in Azure container or in a function or whatnot. Integrated vectorization always runs in Azure servers, which I would say is a plus for it. It's always nice to be able to use powerful servers to run a bunch of ingestion code. In terms of the format supported, they generally both support a lot of formats, although they go about it different ways. But they generally both support quite a lot of formats now. One of the advantages of our manual indexing code right now is that it does store the page number of the PDF for citations. Currently, the built-in skill for splitting in AI Search does not store the page number. That's actually been the biggest reason why people don't use it, at least with our repo, because people really like having that PDF page number. So that's something to keep in mind as to whether a PDF page number is really important to you, in which case you'll need our manual code. And then the manual indexing does token-based chunking. By default, the integrated vectorization does character-based chunking. That's probably only going to be an issue for you if you are dealing with lots of different languages that aren't English. Our manual indexing code also supports other features that we've been experimenting with, like multimedia data ingestion and data access control lists. Whereas the built-in skills in AI Search, they don't support any of those repo-specific features since these are generic skills. If you want to customize our manual indexing code, you just change the Python code. If you want to customize integrated vectorization, you need to make an Azure function, deploy that Azure function, and set that up as a new skill. However, the big drawback of our manual indexing code is that it has to be run manually and run on your machine or wherever you've set it up, and that could be a pain. Versus the integrated vectorization running on the Azure servers with the indexers. They can run on a trigger or periodically using, there's like a format where you can set up your scheduling for indexers. So those are your two options for this repo, but also generally when you're setting up RAG ingestion pipelines. There's some other ways you could set up ingestion pipelines as well. We talked about Fabric. I know some people have, set up their ingestion pipelines in Fabric. I know people have done it in functions, container apps. So there's actually lots of ways you could set up your ingestion pipelines, but this maybe gives you an idea for the things to be looking for and keeping in mind when you're considering what to use. I see a question from James. When using integrated vectorization, do you know when page numbers with citations will be supported? Yeah. I'm trying to remember. I did just talk with Matt about this last week. I think so there is this new skill that came out in November, which is the document intelligence skill. And I think we do have code that shows how to use that skill to pull out page numbers. But there was some reason why we weren't quite ready to use that in our repo. So I think what we're going to end up doing for, at least for this repo, is to turn our indexing code into an Azure function so that it can easily run as a function and be tied into, an indexer skill set pipeline can be used as a skill. I think that's probably what we end up doing, because it's just hard, because as soon as you start changing your document extraction or your splitting, like that can change everything about how your data is stored. So you really want to be consistent with it. So I'm not sure we are actively working on improvements, both to the repo and also generally. There's a question like, okay, if the in a PDF, so from Venkata, in a PDF, if the document has tables and images, is that supported? So document intelligence is very good at extracting tables. For images, it will OCR, so it means it'll extract the text from the images, but it won't, take anything else out of it. However, tomorrow we've got another live stream where I'm going to talk about 2 different approaches for how to handle documents with images. So come back tomorrow, and we're going to talk all about images. And I've got 3 different demos you can try out for that one to see the different approaches. Venkata also asks, is there a solution to chunk Word, PowerPoint, and Excel files? Yeah, so we're already doing that with both of these can chunk those files. So the first step is just they get extracted as text, and then they go through the splitting algorithms. So we're already doing that for both of these approaches. Okay, let's see. I don't know if I've kept up with all the questions here, but let me see. Let's just quickly talk about more AI search features and then tackle a few more questions. So AI search also has something called analyzers that you can use for further customizing how your search is processed. You definitely, if you're doing non-English, you definitely want to consider doing a non-English analyzer. So maybe you can, if you're always doing Spanish or Japanese, you might want to say like, okay, always use the Spanish or Japanese built-in analyzer, but you can also use your own custom analyzer. So that might be useful if you're dealing with data in a particular domain, which has like this really particular way of, writing IDs or product names or something like that, right? So that's something to keep in mind, is that you can fully customize the analysis portion of the search. Next thing is scoring profiles. This is a way that you can boost a search score based on custom parameters. And this is used a lot when you have multiple fields and you kind of want to weight how different fields are considered. So that's something to keep in mind as well for more customization of the scoring. And then this new feature is built-in query rewriting. This came out in November. And this will take the search query and it'll turn it into like however many you want, like 10 different queries, and it'll use those behind the scenes for doing the search. So this is particularly useful if you're not using vectors, because it kind of does the same thing as vectors, like trying to come up with semantically similar things. And also they saw that this got better results for hybrid retrieval only in like the kind of the hardest of scenarios, so low recall scenarios as they're called. So I actually haven't used this yet in the repo, but we might add it in as an option for those to try it out to see if it improves your results. This actually uses a small language model behind the scenes in order to come up with these queries. So it's quite fast since it's a small model that it's using. And then for those of you who are storing lots and lots of vectors, Azure AI Search has tons of options for reducing the storage space. So they've added the ability to quantize and do integer byte quantization, binary quantization, and really reduce the amount of space. So that's something to look into if you are storing billions of vectors. All right. So there we've talked a lot about AI search. Let me look at a few more questions. And let's see. Okay. All right. Trying to see if I missed anything. Oh, Anthony has asked a question. Would it be optimal to convert to Markdown first before chunking XML-based files using something like Markdown? That's a good question about ingesting XML files. I haven't looked into the if there's any research on that. So what we generally find is that LLMs are pretty good at Markdown. They're also pretty good at HTML. There was some research. I think the research actually showed, I think they're actually better at even at HTML than Markdown, but they're generally pretty good at understanding both Markdown and HTML. So a lot of folks will use that as like an intermediary. Like if you don't use document intelligence, another thing you could use is PyMu PDF for local PDF extraction. So that, and they even have a special function that'll take a PDF and it'll turn it into Markdown, because it's such a common use case to want to take a PDF and turn it into Markdown. So it's probably a good thing to try, but also LLMs they know XML and they know HTML. So I think you'd probably want to just compare and see, and also see if anyone's done the research already to compare the understanding of those. And we didn't talk about semantic chunking. You can also do something called semantic chunking, where and this is something you can do. I think LangChain has some packages for it, but basically, like, semantic chunking would take a document and say, like, okay, we're gonna preserve, this is a whole section about a similar topic. That's all gonna go in a chunk, right? So it's a really nice approach. The hard thing is just, what happens when the chunks are too big. Like you still need to have token-based chunking too. But that would be another thing to consider is, semantic chunking, or maybe structure-based chunking, like with an XML file. Can you kind of do like a structure-based chunking so that it makes sense in the results? All right. I see. Apparently there was a 500 billion AI investment announced today. I did not see that announcement yet, but I will look at that after. All right. So let's talk about next steps. Tomorrow, we're going to be talking about multimedia data ingestion, 2 different approaches we have for that. And that's really going to be building on this, what we talked about today. And we've got lots of upcoming streams coming up after that one. So please register for the whole series. I do also have office hours every Thursday in the AI Discord. I see a comment that link isn't working. So maybe that was the one from last week and it expired. So maybe we have to update it. But basically, if you find the let me see if I can find the Microsoft AI Discord link. It'll just be in the Microsoft AI Discord. Let's see if this one works. Let me try this one. So if you can find that Discord, then you'll see it in the events, and then you can join it. I hope that invite works since we just popped it up. I see. Okay. So we'll need to update that link to one that doesn't expire. Thank you, Yash. All right. So thank you, everyone, for the great questions and comments. And thank you again, Hannah, for sharing your search expertise.
Thank you.
All right. Bye, everyone.
Bye.
Thank you, everyone, for joining. Thank you so much to our speakers. Our session is a part of a series. To register for future shows and to watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can also find that link on the screen or in the chat. Today's event code is 24572, and we will see you at the next one.